All right, welcome everybody. So in this video, we're going to first define what a symmetric matrix is, and then we're going to review how we diagonalize matrices, and in particular, what's going to be special about the diagonalization process when we're working with symmetric matrices. So a symmetric matrix A is a matrix such that the transpose of A equals A. And so as a result of that definition, by default, we get that A has to be a square matrix. So a square matrix such that when we take the transpose of that matrix, we get the same matrix back. That's what we call a symmetric matrix. So as a result of this definition, we'll see that the entries on the main diagonal, there's going to be no restriction on them, but for all of the off-diagonal entries, they're going to come in pairs. So for each value above the main diagonal, we're going to have a corresponding value that goes in a very particular place below the main diagonal. So let's take a look at a couple of examples of symmetric matrices. So this 2x2 matrix, whose first column is 1, 2, and whose second column is 2, minus 4. This is symmetric since what we want to make sure is that the off-diagonal entries are mirror images of each other. And what we mean by that is that element A12, which in this case is equal to 2, that should equal element 2, 1, which it does. So this is a symmetric matrix. The next 3x3 matrix, where the first column is 1, minus 2, 7, we have minus 2, 12, 5, and 7, 5, minus 17 as the last column. This is also a symmetric matrix because each of these entries comes in pairs. So for A12 equals minus 2, we see that A21 is equal to minus 2. A13 is 7, so we want to make sure that A31 is 7. And A23 is 5, so we want to make sure that its mirror image, A32, is 5. So we're just kind of reflecting these values over the main diagonal, and the main diagonal entries, they can be anything. Let's take a look at some examples of matrices which are not symmetric. So this first 2x2 matrix, 1, minus 2, 2, 4, this is not a symmetric matrix because these entries above and below the main diagonal, they differ by a sign. So they need to be equal to each other, not equal to each other in absolute value. And if we check this 3x3 matrix where we've got the first column 1, 0, 0, 0, 1, minus 1, and then minus 1, 0, 1, we can check all of these conditions again. So we've got that A12 is equal to A21. Great. However, A13 does not equal A31. So here, this is off. That's enough to rule this out from being symmetric, but also in this case, A32 is not equal to A23. So this one is not a symmetric matrix. Okay, so this will be a short video. I just want to make sure it's clear what a symmetric matrix is. I'm gonna do a quick little recap of diagonalization of matrices before we take a look at what's special about diagonalizing a symmetric matrix.